Kia ora tātou, we're just going to go through the Level 2 2023 Electricity and Electromagentism paper. Paper's just been released online. Check out mechanics, I've done that one as well. I'll do waves a bit later. Okay, I'm going to need my pen. Show that the value of the electric field strength between the plates is 240. Okay, so you look at your formula sheet and you're going to notice that electric field strength is equal to voltage divided by distance, which equals 12 volts divided by 0.05 meters, which equals 240 volts per meter. So volts per meter is your thing. Okay, draw the electric field lines. Okay, so if you notice, this is the positive end of the... Oh, why is that massive? This is the positive end of the battery up here, and this is the negative end, which means that this will be the positive plate and this will be the negative plate. So your field is going to go from positive to negative, and it's going to look a bit like that. And make sure you have the curved ones on the end. Okay. Explain how the electric force would vary as it moved from the negative plate to the positive plate. So, negative. So the electron is a negative charge, and as such, it's going to want to go to the positive plate. So, it's going to fly from here to here, but the force is equal to the electric field strength divided by the charge. Now, the charge is constant, and the electric field strength is the constant. Both are constant, which means that the force does not change at all. And this is because it is a uniform field. So the force does not change. So the electric force would not vary. There's a lot of sort of trolley questions in this paper. They try and trip you up. It's a bit mean. An electron has moved from point A to point B. Okay, now this is the positive plate. I want those. Those are in the way, aren't they? This is the positive plate. This is the negative plate. So notice we've actually moved the electron to towards the negative plate, which it doesn't want to be. So at the positive plate, it has 0 potential energy at point A, because it doesn't want to move any further. It's perfectly happy where it is. It's already at the positive plate. It's not going to fly towards the negative plate. However, at point B, energy potential is equal to E QD. The electric field strength is 240. The charge on an electron is 1.6 times 10 to the minus 19, and the distance is 0.05 meters. And if you put this in your calculator, 240 times 1.6 times 10 to the, I think that's the charge on an electron, could be wrong, times 0.05 meters, you're going to get 1.9 times 10 to the minus 18 joules. So not many joules, but enough. Right. The electron is now moved from C to point D. Now, you'd think it's the same answer. EQD, D is this, but the distance is calculated by change in distance from positive to negative. And you notice at C and D, they are the exact same distance from each plate. So no change. C and D are both the same distance. They're both the same distance from each plate. They both have the same potential energy. And then essentially this question is just sort of a rehash of the previous two questions. You just have to state that A to B, you're moving between the plates. You're moving closer to one plate and far away from the other one. This one, you're not moving closer to either plate, so there's no change in potential energy. Okay, question 2, circuits. Okay, the top section has an element. Okay, so you're going to bust out a pop a formula sheet on this one, and you're going to notice that 1 on the total resistance is equal to 1 on 6.2 plus 1 on 4.2. Therefore, the total resistance, you're going to add those two fractions together in your calculator. 1 on 6.2 plus 1 on 4.2, and then you're going to raise it to the power of minus 1, and you get 2.5 ohms. Okay, the current flows the power supply to the oven when both sections are working. Okay, so we have to calculate the resistance of this pit down here. Okay, so bottom section, why is it massive all of a sudden? 1 on RT, 1 on this total resistance, is equal to 1 on 8.2 plus 1 on 4.2. Therefore, the total resistance of that bottom section is equal to 1 on 8.2 plus 1 on 4.2 raised to the power of minus 1, 2.77 ohms. Therefore, the total resistance is equal to that plus the 2.5 ohms that we've already calculated. It's going to be 5.28 ohms. Now we know our voltage is 12 volts, and we know this can go away, and we know that V is equal to IR. So I is equal to the 12 volts divided by the 5.82 ohms, 5.28 ohms. You're going to get 12 divided by 5.28, 2.27 amps. So that is the current flowing from the power supply, 2.27 amps. When both sections are working correctly, the lamp in the bottom develops a fault and the resistance increases. Minus the other lamp. Okay, so I'm going to go back to this. And so we got, I'm just going to write down our 2.27 amps. Just so we don't, we don't even need that, it's useless, but whatever. Okay, what it's saying is, suppose this number decreased. What would happen to the brightness of that bulb? Okay, so what you're going to show is that a decrease to the resistance here, recall that the resistance total of this part of the circuit is essentially 1 divided by 1 on 1.82 plus 1 on 4.2. If you're not too comfortable with fractions, I suggest you go and see what's happening here. Essentially what it is it's saying 1 on RT equals 1 on 8.2 plus 1 on 4.2, and then I'm dividing everything through by that, or flipping the fractions upside down means we can write it like this. Anyway, RT equals yada 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 is proportional to the, it's inversely proportional to the addition of the inverses of the, it's a bit ugly, but anyway, a decrease to 4.2 means that this fraction here will increase, because a lower number on the denominator means a higher fraction. An increase to that means an increase to this entire bottom fraction, which means that the actual total resistance of that section will go down because this bottom section has lowered. No, it has increased. Wait. Ugh. Okay, 4.2 goes down, which means that this bottom whole thing gets bigger, which means the total resistance goes down. Yeah, total resistance lowers. Which means, ladies and gentlemen, that the total resistance of the circuit goes down. Now, it's still 12 volts. We've reduced this, which means we must increase the current. So there is now more current flowing through the circuit. Now, I don't. Now, this is enough of an argument, but you could go a bit step further, and you could show that in this top section, the resistance, the voltage across that lamp will actually increase. It will have a higher voltage, but you probably don't even need to say that, because once you've set the currents higher, you can jump straight to power is equal to IV, and say an increase to the current, and therefore more power. More power equals brighter. So this lamp will shine very brightly. It will shine even brighter. The lamp in the bottom section now stops working. Counting the amount of... Okay, I actually got this wrong on the exam because I misread it a bit stupidly. So this lamp here, goodbye, stops working, which means this is no longer parallel, it's series, because no current will flow through this branch, which means that the total resistance of the circuit is now 8.2 plus the 2.5, which is 10.7 ohms, which is a drastic increase. It's almost double, which means that current is equal to 12 volts divided by 10.7 ohms, 12 divided by 10.7, 1.12 amps. Now, if that's 1.12 amps, that is flowing everywhere in the circuit. Okay, so 1.12 amps in total will flow across this, 1.12 amps will flow across the 8.2 ohms resistor. Now that's crucial because it wants the heat, so we're going to need the power. But first we need the voltage. The voltage is equal to 1.12 times by the 8.2 ohms, which is equal to 9.2 volts. Now the power is equal to volts times the current, which equals 9.2 times 1.12, which equals 10.3 joules per second. Now I'm not writing this as watts, I'm writing it as joules per second because it wants the amount of energy in 2 minutes. If we've got 10.3 joules per second, that means we have 618 joules per minute, or timesing that by 2, 1236 joules in 2 minutes. That's the answer. I put 300 because I misread it. That sucks. A lot of people struggle with this one. I'm pretty sure I know what to do, but correct me if I get it wrong. Draw an axis on the diagram above to show the direction of the magnetic force. Okay, so the power supply is switched on. This is the positive plate, and this is the negative one, because it's got the smaller, this is the bigger one, which means the current flows this way. Okay, now you're going to remember the right hand slap rule. Your thumb is the current, your fingers are coming out of the page, which should lead you to proclaiming the force is this way. Okay, to calculate the strength of the magnetic force, so force equals BIL, and I is equal to V on R, which is 120 volts, divided by the 42.1 ohms resistance. You're going to get 2.85. You could just sub this directly in here, BVL divided by R, but okay. And now people were tripped up on what L to use. Now for this one, the force is generated due to the flowing current. The current is only flowing between these two branches. It's not flowing up here. I don't think so, at least. It's just flowing around here. It's not flowing in these end parts, which means that you want to use this. Now, I'm not actually 100% certain on that, but, check it. Okay, so the force is going to be equal to the 8.1 times 10 to the minus 3 Tesla. 10 to the minus 3 Teslas. Times the current, which we just worked out, times 2.85, times the length, which is 0.84. I mean, you definitely don't want to use this whole thing. That's definitely not it. Force equals 0.019 newtons. Bingo bango. The meter axis is given a push that's moving to the right. Okay, so induced voltage time. You're going to bend on the axle. Okay, you got to remember the other right-hand rule. Your thumb goes towards the direction of motion. Your fingers will come out of the page, and the slap you should come downwards, like this way, which means that the positive charges go to this end and the negative charges go to this end. That is in the wrong color. Positive charges go here, negative charges go here. So negative, positive. Calculate the voltage induced. Okay, voltage equals BVL. Now, here's why I like the L, because now you would use the 0.95 because that's the total length of this. So I think the way they've done it is to use one for one and one for the other. So that's why I'm reasonably confident. So it was 8.1 times 10 to the minus 3 Tesla. You just have to remember that from the previous page. Times the velocity, which is 3.1. Times the length, which is now 0.95, and you should get 0.024 volts. Two significant figures. Describe the motion of the axle. Okay, so this is just a simple one. You've got to explain what's going on. This is the hardest question in the paper. You've got to really think about it. When this is set moving, we're going to get positive charges here, negative charges here. So there's going to be a current flowing around the circuit like that. Okay, now that means the current is flowing down here. Now you use the slap rule. You got your thumb with the current, your fingers coming out of the page with the field. A force is going this way. And so the force opposes the motion. So it will decelerate and stop. That's the answer. Now you have to justify why that is. Okay. Voltage is induced due to separation of charge. You would say induced current. Okay, so